on to chapter 5, 5.3 and 5.4, the distribution of the sample mean is where the rubber meets the road in this class. So things are about to get real. We're about to embark on the statistics that you don't learn about in grade school. We're about to make use of everything we've spent this semester learning thus far. We've built up all this machinery. Now let's start using it for the purpose of statistics. The basic idea of what we're going to be doing for the next 5 weeks is that of statistical inference. So statistical inference is the process of attempting to understand something about a population by looking at samples from the population. Populations are typically thought of as large, potentially even infinite, but in general, they're usually considered to be large, often too large for it to be practical for you to have access to the entire population's worth of data. So you take a reasonable sized sample from the population and see what you can figure out about the population. Typically, what we're interested in is population parameters, such as the population mean, or maybe the population standard deviation. Or it could even be some other thing, parameter of the population. So today we're going to focus on the mean. We're mostly going to be focused on the mean. That's by no means the only thing that you could be, in theory, attempting to infer. So on the homework for this week, I asked you to infer something other than the mean, actually the inverse of the mean. I asked you to infer the rate parameter of an exponential distribution. That's not the mean. The mean is 1 over the rate parameter, so it's a little bit different. So just a heads up, I'm giving you a different type of inference question on the homework, and I hope I explained it well enough on the homework. Back to what we're going to be doing in lecture today. Suppose, for example, I would like to determine the average IQ of BSU students. Okay, so this would be an example of inference. Suppose I attempt to infer the average IQ of BSU students. Inference would mean doing this by looking at samples of BSU students. Say I look at samples of 6 students at a time. Now, let's say I took a sample of 6 BSU students, like 1, 2, 3, 4, 5, 6, like these 6 right here, and I found their mean IQ. What is my guess for what the mean IQ of all BSU students is? Yeah. I did say that IQs are normalized over the globe to have an average of 100. So it would be a good guess if I was randomly sampling global citizens. But here I'm focused on BSU students who may not necessarily have the same mean as the global IQ. And if I'm only looking at 6 of them at a time, you might think that, well, just take the average IQ of those 6. For lack of any better information, that would be your best guess for the mean IQ of all BSU students. But if I took 6 students in the same class or in the same major, or that knew each other, or that sat next to each other, as these 6 here are, that may not be representative of BSU students as a whole. Maybe students that take Math 360 do not have IQs representative of BSU students as a whole. So what I need to do to account for this potential source of bias is collect what's called a simple random sample. This is the most common method of sampling. And a simple random sample, also abbreviated SRS, is where the observations in your sample are independent and all drawn from the same distribution. So that would be like choosing 6 students from the population of BSU students, where all students are equally likely to be chosen. So they all have the same distribution, namely the distribution of IQs of BSU students, and they're not dependent. So I don't be not choosing people from the same class or that know each other or that are brother and sister or that live in the same house. They should have no relation to each other. Knowing anything about any one of them should give me no information about any others. When you do this, by the way, you could also describe such observations as independent and identically distributed. This is a phrase that is used more common in the probability context. It means the same thing as simple random sample. Since this is a statistics class, I will try to use SRS or simple random sample instead of saying IID, which means independent and identically distributed, but they mean the same thing. Now, there's one little hitch on this topic of independence, and that is the case of sampling without replacement. Usually, when you think of a sample, you're probably not in your head imagining the possibility that the same person could appear more than once in your sample. I mean, you could, that actually is a method of sampling, but often in practice, in the real world, you don't sample with replacement, right? Like if I was choosing people to find their IQs, I'm probably not going to choose the same person more than once. I could, but if you don't, if you're sampling without replacement, then strictly speaking, the observations are not independent, because once you've chosen one person from your sample, the population distribution has been altered ever so slightly. Nevertheless, as long as our sample sizes are a small enough proportion of the population, we're going to ignore this and pretend that independence holds. So we are, for the most part, going to ignore this issue and just assume that our samples, if drawn without replacement, are independent, as long as the samples are less than, say, 5% of the population. Okay, so back to the BSU IQ inference example. My goal is to determine the average IQ of BSU students. I'm going to accomplish this by taking samples of 6 students and finding the average of their IQs. Let's see, let me ask you these 3 questions on Socrative. So please answer on Socrative the following 3 questions. What's the population of interest? What parameter are we attempting to infer? And what's the sample size? Okay, yeah, so it looks like people are correctly getting that the population of interest is that of BSU students. The parameter we're attempting to infer is the mean IQ of BSU students. And the sample size is 6. Here's what one of those samples might look like. So that's a sample with 6 observations. I can compute the mean of that sample. Comes out to be 106.35. Let me alter this sentence. If these are simple random samples, then these values are random. Right? And this procedure is a random process or a random trial, and you can repeat it. Even if you don't repeat a sampling process in practice, you should imagine in theory that it gets repeated a very large number of times. In theory, an infinite number of times. So I could, in theory, take a second sample, and I get 6 other random observations yielding another sample mean. This time 109. Oh, dang, I got a 132 in that one. Oh, yeah, that sample is definitely from 360 students. So these are random. Is their mean random? The observations are random. Well, it looks like the mean is the average of 6 random numbers, so it too is a random number, and understanding its distribution is the main goal of today's lecture. So, as I was saying, in treating samples at random, we are implicitly assuming that this sampling procedure is an experiment which could, at least in theory, be repeated over and over and over and over a very large number of times. Sometimes on the homework, you'll simulate a sampling procedure 10,000 times, but you could get even better results if you did it 1,000,000 times or a zillion times. At that point, though, it becomes computationally impractical. And what we're trying to analyze is the sort of distribution the sample means have after many such repetitions. Like, for example, if I repeated this sample, take a sample of size 6 procedure described above and plotted a histogram of the resulting sample means, I might get something that looks like this. This is what we're after today. What's the shape of this distribution of the sample mean? Well, what's the mean of the distribution of the sample mean? What's the standard deviation of the distribution of the sample mean? That's what we're going to be talking about today. So now let's talk more generally about an arbitrary simple random sample, x1, x2 up to xn, drawn from some arbitrary distribution. I say arbitrary, it will be fixed though. In this class, we treat population distributions as fixed. Here's a true or false question. And I have a number of these true or false questions to make sure you're following along with the setup that I'm describing. In this setup, true or false, the x sub i's are necessarily independent, and each one of them has the exact same distribution. So why don't you answer on Socrative? True or false? I take a simple random sample x1 through xn from some distribution, Are the xi's necessarily independent? They all have the same distribution? Hey, nice. All right. Yeah, 2/3 of you got it. I think I faked out almost my whole class last class. All right, but you guys are on the you guys did better because the answer is yes, because I said it was a simple random sample, which is exactly the statement that they're independent and with the same distribution. This is precisely what it means to say they are a simple random sample. Okay. A quick note about notation. So as usual, we're going to use uppercase letters for random variables. I don't think this comes up today, but we'll use or often use lowercase letters for specific values of random variables. So let me just show you what that could mean in the previous example. So back when I was taking samples of size 6 from BSU students, the first observation would be capital X1, the second would be capital X2, etc. The last one would have been capital X6. And here you can see possible values that capital X2 ended up equaling. Like apparently, one of the values was 100. That would be considered a value in the sample. We might use a little x or little x sub 2 to equal 100, but the capital X is a random variable. Now, for this class, for our purposes here and now, and next 5 weeks, I think for the rest of the class even, we'll always assume the population distribution is fixed. If and when you take higher level statistics classes, you may learn about the Bayesian approach to statistics, where you start treating population parameters as random variables. In this class, we treat the population distribution as fixed, which means its parameters are fixed as well. We may not know what they are, but they're out there, fixed, sitting at some, in theory, knowable number. Okay, so the sample mean of our simple random sample is the sum x1 plus ... up to xn divided by n, and we will denote this x bar. And today we're going to study its distribution, sometimes called the sampling distribution. So today we're focusing on the distribution of the sample mean, and clearly it's going to depend on the underlying fixed background population distribution. So I'll show you some examples of different population distributions, but first, let's come up with some equations, no matter what the background distribution is. So let's come up with some equations for the expectation and the variance of the sample mean. So suppose x1 up to xn constitute our simple random sample of size n, drawn from some arbitrary distribution with mean mu and standard deviation sigma. First, true or false? The x sub I in this setup are random. Go ahead and answer that. Okay, good. Yes, everyone's getting. They are random. I mean, I said they're random right there. Okay, next true or false question. True or false? Mu and sigma are random. Go ahead and answer that on Socrative. Mu and sigma are the mean and standard deviation of the background distribution. And we're treating the background distribution as fixed with fixed parameters that may not be known to us, but are in principle knowable, which means that they are not random. In this class, up until you get to Bayesian statistics, which is a couple classes past this one, population parameters are fixed. So no, these are some numbers. Even if we don't know them, they are in theory out there, fixed and knowable. Again, to make sure you're following along with the setup described here, true or false? The x sub I described above are normally distributed. Go ahead and answer this on Socrative. See, so yeah, so where did I say they were normal? If I give you that a distribution has mean mu and standard deviation sigma, that means it's normal, right? There's no other distributions that have a mean and a standard deviation, right? Or does every, wait, or does every distribution have a mean and standard deviation? Well, did I say these were normal? Where's the word normal on the screen? I don't see it anywhere. No, they don't have to be normal. Now, you could be forgiven for thinking so because I did use the letters mu and sigma, which certainly are parameters of any normal model, but also of any other model too. Like every population has a mean and a standard deviation. So yeah, this does not, the background distribution does not have to be normal. I didn't say it was, and it in general will not be. This one's a no. Oh, I faked out 80% of the class. All right. Yes.
So in general, then we assume unless it's otherwise stated.
So we're going to learn a theorem today about when something is normal. That's a good question. Let me get back to that at the end of class today. Okay, so as I previously mentioned, we defined the sample mean to be, well, the mean of the sample, right? The sum divided by the number of terms in the sample. So let's see, I think you all, or most of you hopefully would agree that the sample mean is random. I mean, even if you didn't know that, it's written with a capital letter, so it probably indicates that it is. The fact that it's a average of random variables. Yeah, right.
What is the difference between X bar and?
Yeah, so for one of them is random. Let's look at this process here. Suppose, okay, does anyone know what the mean IQ of BSU students is? Dylan?
The first sample or all of them?
All BSU students. All right, let's, it's a little bit higher than that. Let's say 103, okay? So somewhere out there is the mean IQ of BSU students. In fact, it actually happens to be 103. So the true value is 103. That may not be known to us, but it's out there and fixed. What we get for X bar is the mean of our sample, which you can see some possible values of it. It's random. It will depend on the sample. So that's the difference between X bar, which is a random variable equal to the sample mean, and the fixed population mean, even if we don't know what it is. It's out there and fixed. That help?
Yeah.
All right. Cool. Yeah, good question. Okay, so first thing may not be surprising. It states that on average, your sample mean will equal the population mean. So this should come as no surprise. It's kind of like saying, well, the best guess for your population mean is your sample mean. And if you make that guess, on average, you'll be right. Because the expectation of X bar is mu. So for now, just accept this. I'll prove it. I believe I'll prove it next class. Time permitting, I'll prove it next class. Okay. I'm not going to do this as a true or false question. So since each of these xi's are drawn from a distribution with standard deviation sigma, that means they're drawn from a distribution with variance sigma squared, right? So the variance of each one of the xi's is sigma squared. Okay. What do you think the variance of the sample mean is? No one's going to get this, by the way, unless they've already looked at the notes, which I did post a pre-lecture copy of, by the way. If you didn't notice, I guess I didn't really announce it, but if you looked for it on Canvas, it was up there. Anyone know what it is? There's no way you could figure this out in your head unless you're a super genius, but maybe someone has already seen what it is. It's not sigma squared. Yeah, Bennett? Yeah, so this is another thing that I'll have to prove next time, time permitting. The variance of the sample mean ends up being sigma squared over n, not sigma squared. So notice that the mean of the sample mean is the population mean. The variance of the sample mean is not the same as the variance of the xi's. Apparently, taking means sort of centers the data. Notice this number decreases when n increases. As a consequence, the standard deviation of the sample mean, well, that's just the square root of sigma squared over n. So that ends up equaling sigma over the square root of n. Okay, so the standard deviation gets smaller as n gets larger. What do you think then the distribution looks like. What do distributions with very small standard deviations look like? Standard deviation is the typical distance of a point from the center. So if that typical distance is very small, roughly, what does the shape of the distribution look like? What's it look like if the standard deviation is 0? That's a spike at a single point. That's where you have a random variable, which is a constant, which is constantly equal to just one value. So small standard deviations are close to looking like a spike. Okay, so what I'm saying is, for large N, the distribution of X bar is highly spiked and concentrated. In particular, it's concentrated around its mean, mu. This is reflected in the so-called law of large numbers, which I like to think about as the statement that statistics works. It just says that if you take a large enough sample, the sample mean approaches the population mean, which is kind of like obvious, right? If I wanted to know the average IQ of BSU students, well, if I ask enough students, I should get really close to the true average. I mean, heck, I could just ask everyone. And then by definition, I would have the true average. So anyway, the law of large numbers states that sample mean approaches the population mean as N increases, the sample size increases. So it's almost an obvious statement. Let me summarize the equations for the sample mean that I've just figured out. So here's a summary of what we've already been doing. Again, if x1 up through xn are a simple random sample, and they're drawn from a background population distribution, mean variance sigma squared, and their sample mean x bar is equation for the sample mean 1 over n times x1 plus dot 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 xn. Then, as I said, its expected value is the population mean, and as I said, its variance is the population variance, but over a factor of n. I can make a similar statement about the total for the sum of the observations. So I don't have to take an average. What if instead I ignored the average part and just looked at the sum? Let's give that a name. How about capital T? So we're letting capital T be the sum of x1 up to xn, which is the same as n times the sample mean. Then its expectation is n times the population mean, and its variance is n times the population variance. Occasionally, it's useful to work with the total instead of the average. They differ from each other just by a factor of n. So depending on the problem at hand, you'll be wanting to work with the total rather than the average. Okay, so are you ready for the most important theorem in the class? Potentially in all of statistics and probability. That is the central limit theorem, abbreviated CLT. The central limit theorem describes what happens to the distribution of the sample mean. Or more generally, how about the sample mean and also the sample total as defined right above. So let's let x bar and t be exactly as I defined them right here. The central limit theorem states that for large n, their distributions become approximately normal. As n goes to infinity, this approximation becomes exact. So in the limit that n goes to infinity, you get exactly a normal distribution. So that's kind of crazy. No matter what wacky distribution we started with, when you start taking means, the distribution of the means ends up looking normal. This is why the normal distribution is so ubiquitous across nature, statistics, science, physics, economics, finance, etc. It's why normal distributions appear everywhere, because almost everything is a sum of a bunch of things. Your stock gains are a sum of a bunch of individual profits. The height of a biological creature is the sum of a bunch of effects of, say, individual genes, or the lengths of individual bones. So this is an extremely powerful and broad and deep and wide-reaching theorem. The proof is relatively hard. I've read it and understand it, although it's beyond the scope of this class. It's a pretty cool proof, though. It's almost crazy how the Gaussian, the e to the negative x squared, comes out of it. Like, that's apparently a very natural function. Like there's something inherent to nature about that function, the Gaussian e to the negative x squared. It's sort of mind-blowing. It's like that would be God's favorite function or something. Okay, so you might ask how large n has to be for this approximation to be a good one. Typically, n greater than 30 is sufficient. But the more skewed the original distribution is, the larger n needs to be before the sample mean becomes approximately normal. Conversely, if the original distribution is highly symmetric, then it doesn't take very many n for the sample mean distribution to be normal. I'll show you some examples of that. First example. So, okay, I'm going to apply the central limit theorem to some of our known distributions. Let's start with the Bernoulli. So, Bernoulli. So, the Bernoulli distribution looks like this. It takes on the values 0 and 1, 1 with probability p, 0 with probability 1 minus p. So only two values, 0 and 1. We say 1 for success and 0 for failure. So let's suppose we have a sample of size n drawn from a Bernoulli distribution. What familiar quantity is the sum x1 through xn? Or let me say, what familiar distribution does this have? Like, for example, suppose n is 4 and x1 plus x2 plus x3 plus x4 is, I don't know, 1 plus 0 plus 1 plus 1. Right, t is 3. We've seen this before. Anyone recognize the distribution of the number of successes or ones in n Bernoulli trials? What distribution counts the number of successes in n repeated tries? Nice. Yeah, good. Yeah, no one in my last class got it. This is going to be on Sunday's quiz, by the way, so you should know it. This is exactly the binomial distribution. Exactly the binomial of NP distribution. Okay. Well, we just learned a theorem about the total T. Right, the central limit theorem applies to both the total and the mean. So what does the central limit theorem say about T? The central limit theorem says something eventually becomes normally distributed. So it says T eventually becomes normally distributed. In other words, the binomial distribution becomes approximately normal for large n. Wait a second. I told you that last class. Last lecture, we learned about the normal approximation to the binomial. And what I didn't tell you at the time was that we were just seeing the central limit theorem in action. Yeah. So last class, we learned that the binomial is well approximated by a normal. That's the central limit theorem. So you didn't realize it, we had already actually seen the central limit theorem. And one other thing about the binomial, because this is going to be important later. If you compute the mean x bar, like for example, right here, we had a success, a failure, a success, and a success. So the mean would be what? 1, 4 of 1 plus 0 plus 1 plus 1, which is 3/4. That just gave the proportion of successes. The reason that's important is there's a lot of practical questions that ask for what proportion is the following statement true? Like what proportion of voters want to legalize cannabis, right? What proportion are going to vote for I don't know, going to Mars or refunding the post office or Proposition 17. There's all sorts of questions you could ask about the proportion of something. So we are going to use this fact later on in the course that x bar is the proportion of successes. The fact that we now see proportions to be approximately normally distributed is super important. It's exactly how poll workers determine how many people they need to poll to start getting accurate statistics. All right, so that's the Bernoulli distribution. Let's talk about the exponential now. So this is a skewed distribution. I went and programmed into R some code to generate the distribution of the sample mean for samples taken from an exponential distribution with rate lambda equals 2 for various sample sizes. Let me show you the code. It's going to help on the homework. So first, this is not something that you need to know, but it's kind of useful. If you want to generate a bunch of plots next to each other, you can use this command right here, which will make a 3x3 matrix in your plots section to display, say, histograms or whatever plots you want to display. So I have just generated 9 histograms for distributions of the sample mean taken from the exponential with rate 2. You don't have to know all this. I used a for loop to write these. I wasn't planning on making you learn for loops, but then actually some students said they did want to learn like some for loops. So maybe in future homeworks, I'll try and come up with some problems that touch on a basic for loop. You don't have to know about it, although it's good if you do know how to write a for loop. The command that I mainly want to introduce here and now is the replicate command. It's something you can use in place of a for loop. It repeats an experiment, or it repeats some process some number of times and stores the results in a vector. Like, for example, if I wanted to randomly sample from the exponential distribution with rate 2, and I wanted a sample of size 10, I could use REXP. And there, I just generated 10 samples from the exponential distribution with rate 2. What if I wanted their mean? Well, I would just do mean of that. But today we're talking about the distribution of the sample mean. So you're supposed to run this experiment many times. In theory, an infinite number of times. You don't want to type this in like 1,000 times. Instead, you could use replicate. So if I wanted to replicate this experiment, let's say 10,000 times, I would use replicate. And let's say, and this will create a vector of 10,000 means, each one being the mean of a random sample from the exponential distribution of size 10. It's obviously too long to print, but if I wanted, say, to give a name to it and perform other computations with it, I could make a histogram of it. So I want you to mess with this here, actually, and get comfortable with this, experiment with it. Here, this is what happens. Here, I just generated a sample mean distribution using the replicate command. Yeah. Something else I wanted to say about that. Yeah, I think there was something else. I forget what it was. Anyway, I'll put this code in the notes so you can make reference to it. All right, so let's look at what happened when I did that to the exponential distribution. By the way, let me remind you of some facts about the exponential distribution. So if x has an exponential distribution with rate lambda, then the expected value of x is 1 over lambda. And the standard deviation of x is also 1 over lambda, in fact. We also saw that the expected value of the sample mean is the population mean, and the standard deviation of the sample mean is the population standard deviation over root n. So in particular, you can see what they should be for this, for these examples. So if x1 through xn are drawn from the exponential distribution with rate lambda equals 2, and x bar is 1 over n x1 plus ... up to xn, the expected value of x bar is the expected value of x, or mu, or 1 over lambda. All right, this is mu, or 1 over 2. And the standard deviation of x bar is, well, let's see. Standard deviation of x is 1 over lambda. So this is like my sigma. So it'll be sigma over root n, or 1 over lambda over root n, or 1/2 over root n. So did I say at the beginning that things were about to heat up? Yeah. So this is where the rubber starts meeting the road in this class. I went through this a little bit fast, admittedly. Okay, we're gonna have time to churn this over, but let me just now look and see if this is represented in our sample distributions. For one, what about when the sample mean is 1? If you take a sample of size 1, and its mean is, you're not even adding anything together, it's just one term. So of course, we're just going to see the original distribution represented in a sample of size 1. That is the exponential distribution with rate lambda equals 2. So nothing surprising there. But as we start taking increasingly large samples, say of size 2 or 4 or 8, the sample means start getting more and more bell-shaped. A sample of size 2 has a sample mean that looks pretty darn close to being bell-shaped, despite the fact that it started off pretty skewed. Certainly by the time we get to a sample of size 64, we end up with a bell-shaped distribution. And just to sort of verify these formulas up here, let me verify this one. From the simulation with n equals 256. So this is the very last simulation that I did. This one. If n is 256, then the standard deviation of the sample mean is 1/2 over root 256. 0.5 divided by 256, 0.0313, which is actually exactly what the simulation produced as well. All right, so the simulation does appear to be in agreement with the theory. So that was the exponential. What about when the underlying distribution is normal? And this relates to Cameron's question. In fact, let me show you, I think, the last problem on the WebAssign homework for this week. Here's the very last problem about Rockwell hardness. So this is a measure of hardness known to have a mean value of 50 and a standard deviation of 1.2. We're asked two questions here about the sample mean for a sample of size 11 and about the sample mean for a sample of size 36. What can we assume is normal? They say in part A, if the distribution is normal, which means apparently we can't, unless they tell us, assume it's normal. They had to tell us that. They told us that for a reason. Why did they tell us that for part A, but not for part B? It has to do with the samples. Nice, very good. So part B has a large enough sample that you can assume normality of the distribution of the sample mean by the central limit theorem. As I said, if n is greater than 30, then you that should be sufficient. For part A, though, this sample size was only 11, so they had to tell us that the underlying distribution was normal. Let me give you the equations for when the underlying distribution is normal. Suppose, and first let me give you a fact. This is an important fact which you should internalize. It's pretty non-trivial. It doesn't look very threatening, but trust me, it's deep. Fact. The sum of normal distributions is normal. Or the sum of normally distributed random variables is a normally distributed random variable. Moreover, so is the average. The average of normal random variables is normal. Okay, so as a consequence, here, let's make this a corollary. If x1 through xn constitute a simple random sample drawn from a normal distribution, we know exactly what distribution their sum and also their mean would have. So I wrote it for the mean. I could do it for the sum. I don't think I'm going to have time right now. By the way, I'm probably going to go over this material again next time. But I just want to give you enough to be able to solve that homework problem on the WebAssign homework. So if we apply our normal distribution equations, namely 1 and 2 right here, apply those to in conjunction with the fact that the sum of normal distributions is normal, as is the average, we find that if x1 up to xn each have a normal mu sigma distribution, then sample mean has a normal distribution with the same mean and with standard deviation sigma over root n. Okay, which is actually exactly what I wrote right here. So let me show you an example of that in action using the elastic modulus. So the elastic modulus of a material is a measure of elasticity measured in pascals. The elastic moduli of the acrylonitrile butadiene styrene, or ABS, which is a polymer. It's a polymer used to construct iPhone cases, known to be normally distributed. That is, the elastic moduli of this material is known to be normally distributed with means mu equals 2 pascals and standard deviation 0.1 pascals. An inspector wants to perform quality control on samples of iPhone cases coming off the assembly line. And he looks at 4 at a time and just checks the mean elasticity to see if it's above or below some threshold. If it's within some range, and he figures that it's all good, but if it's too high or too low, probably going to throw it out. So let's find the probability that he observes a sample mean of greater than 2.06 pascals for these samples of size 4 from a normal distribution with mean 2 and standard deviation 0.1. So the sample mean, so sample size n is 4. Mu is 2, sigma is 0.1. What's the distribution of X bar? Yeah, right.
Would it be 2 and then 0.05?
All right. Yes. So the mean is still the same mean, as I said right here. The standard deviation is sigma over root n, which is 0.1 over square root 4, which is 0.05. Oops, this is our 2. All right. So now we're asking for the probability that X bar is greater than 2.06. This is now just a question about normal distributions. You can either standardize or not standardize. So probably the most direct way to answer using R would be P norm 2.06 with mean 2 and standard deviation 0.05 and lower tail equals false, which comes out to be about 11.5%. Alternately, you could standardize. You could also do P norm of what? 2.06 minus 2 over 0.05. That would also work. That ends up, that's P norm of 1.2. And if I plug that into R, you should get the same thing. Also 11.5. Okay, cool. So I hope that addressed Cameron's question to the extent possible. You now see that you can't necessarily assume things are normal, but if the central limit theorem applies, then you can. So the averages and the totals. Otherwise, though, you shouldn't assume it unless they tell you. Cool. All right. Thanks for coming. Have a nice weekend. The Broncos playing this weekend?
No, this is my week.
Did anyone see how the Bears game ended last night?
Yeah.
Oh man, that sucked. He caught it, but then bobbled it as he fell out of the end zone.
That was great defense, though.
Yeah. Yeah, yeah, right, that should, no, I didn't watch most of it, but I'm glad I watched the last one.
Yeah.
Well, I have two questions. One is not related to class.